This lecture is going to focus on some more formal approach to machine learning. This will be a bit difficult, this lecture, but remember that you don't need to memorize the equations and the formula. The idea here is to understand these concepts, and what we're going to do is to look at machine learning on a more formal level and see some results that we can obtain from intuitions that we've been encountering so far about trying to generalize from the training set to outside the training set, these problems of bias and variance and the source of errors and so on. So we're going to start with some concepts, this empirical risk minimization and probably approximately correct learning, and we're going to see how we can derive some boundaries for the errors we get in our classifiers, both for assuming we have hypothesis class that are finite, that we can enumerate all the individual hypotheses, or then with shattering and the Vapnik-Chervonenkis dimension, we will see how we can extend that to a continuous parameter space where we have actually an infinite number of hypotheses. So basically the idea is that we've been seeing these concepts, error, bias, variance, underfitting, overfitting, and so on. And in practice, the way we select the best classifiers empirically is by doing, for example, cross-validation. This is reliable, it's very easy to do. We don't actually do things like bias variance trade-off in practice when we are selecting classifiers. So that is one aspect of that we covered here, that is to help understand where the error comes from. And what the approach we're going to take here in this lecture, more formal approach, is not for a practical purpose, but it's useful to understand some probabilistic concepts underlying machine learning. So let's start with this idea, empirical risk minimization. If you look at the literature on these foundations of machine learning, you're going to find this concept. And the idea here is that we have some loss function that measures how bad our predictions are. So this may be, for example, the quadratic error we saw in regression, or the Breyer score, or the percentage or the fraction of incorrectly classified examples, things like that. And the risk is the expected loss. So our risk would be what on average we are going to lose or to have in this measure when we try to classify examples. Now, the empirical risk is the actual average loss we can measure. This is, for example, in our data, in our training set or something like that, we can measure what on average is the loss. Remember that loss here, we are thinking of it as a generic term for any measure, for example, of error or something like that. So it can be the quadratic error, Breyer score. This is an abstract concept. Empirical risk minimization is the approach of trying to find the hypothesis that minimizes the risk, the empirical risk, that is the loss on the training set. But there is this true risk. This is a more general idea than the true error. It's not just a measure of how many mistakes we make, but it's any function that we consider to measure how bad our predictions are. So the true risk would be the average loss over all possible data. And we saw so far intuitively that the empirical risk, the loss that we are measuring on average on our training set, will underestimate the true risk, because we are fine-tuning everything to minimize specifically the loss on our training set. So this is a more abstract approach to this idea that we found of the training error, the true error, and so on. Now, to obtain some boundary, some idea, or at least some limits to the probability of making more than a certain number of mistakes, or some boundaries on these risks, we're going to need these relations from probability theory. So the first one is fairly simple. If we have a set of random events, then the probability of any one of those events happening, so either A1 or A2 or something, or any of the other, is not greater than the sum of their probabilities. So it's the sum of their probabilities if they are all mutually exclusive, but if they are not, then the probability of any one event happening will be smaller than the sum of their probabilities. So this is the union bound. This is just a relation that we have from probabilities. Houghton's inequality is also something that we're going to use later on, so I'll just get rid of it now. This relates the probability that the true probability of some event, which these are Bernoulli distributions, so it's something that either happens or it doesn't. We can think of that as like making a mistake in classification or classifying some example correctly, something like that. Either we do it or we don't. And we have this probability phi of getting it right, for example. We can measure in a sample. Suppose that these are the classifications of our training set. We can average how many times we get things right in our training set. So this would be an estimate of the probability of, for example, classifying an example correctly. Note that this is more generic. This is for any Bernoulli type variable, but we can think of this now as in our classifier, making mistakes or not. So this Houghton's inequality gives us the boundaries on the probability of our estimate deviating from the true probability of, for example, making a mistake. So this would be the true error. This would be our empirical estimate, for example. And the probability of these two being having a difference greater than some gamma is smaller than this expression, 2 times e raised to minus 2 gamma squared m. So the expression itself is not very important, but the idea is that this is an exponential function and this decreases as m increases. M is the size of our data set. So this is a more formal statement about this intuition that the larger our training set, the closer our estimate of the error will be to the true error. And this is intuitive. If we have more data, we can have a better estimate of the true error. But this Houghton's inequality sets this boundary in a more rigorous manner by telling us that the probability that the deviation is larger than some factor is this expression, and it decreases with the size of the data set that we have. So now let's think about binary classifiers. In this case, we have some universe of points, X, from which we can extract examples. And we have binary classifiers that can map any example into 0, 1. So they classify either on class 0 or class 1. And we have a sample S of a number M of examples that we've taken from this universe with some random distribution. That is, we are sampling from the universe to get our data. Now, the empirical error, the training error, is basically the average of the mistakes we are making when trying to classify in our data. So the empirical error is the one here with the hat, the one we are measuring for some hypothesis H, is the sum of adding 1 every time we make a mistake. That is, our hypothesis is saying that the point belongs to a class that is different from the actual class the point belongs to. And this sum divided by the number of points tells us the fraction of errors we are making. The true error would be the probability of making a mistake, predicting a class different from the real one, for any point that is drawn with this distribution from our universe. So this would be the true error. If we take a point at random, what is the probability of making a mistake? Now, this one we cannot measure. This is the one that we can measure because we have this sample of points. So suppose we have a binary classifier. We can adjust the parameters to move along the hypothesis class, to select any hypothesis. And we are going to select the parameters by minimizing this training error. That is, we're going to minimize the empirical risk. In this case, the loss is just the error, and the risk is the average loss, and it's empirical because we are measuring on the training error. So we are fine-tuning the parameters in order to find the best parameters defined by this expression. We are minimizing the empirical error. Okay, so in general, this is an NP-hard problem. We can approximate it. We have these, for example, stochastic gradient descent that we saw in neural networks, in different approaches, but we are trying to do this. So let's assume that this is what we can actually do in our learner. Sometimes it's not. Sometimes we cannot really guarantee that we find the maximum, the minimum in practice. But let's assume that in abstract we have some learner that can actually find the set of parameters that minimize the empirical risk. And now we can get an idea, boundary of the true error using Hoeffding's inequality. So that relation between what we are estimating and what is the true error that. So that would be a general idea here, a general approach, but we're going to look at this in the context of this concept, probably approximately correct learning. So let's suppose that we have this universe of possible examples. We have a target function to learn because each example has a class. And we have this hypothesis class from which we are going to choose the best hypothesis. So we're going to minimize the empirical error, the empirical risk to choose the best hypothesis. We are taking a sample. Our training sample is taken from the universe of examples with this distribution. And we can also then test with another sample, for example, using the same distribution and so on. But the idea is that during learning, we have a sample of examples taken from the universe with some distribution, random distribution, and we are going to select one hypothesis from the hypothesis class by minimizing the empirical error. So this is what we saw, empirical risk minimization. This is what our learner is going to do. Now, the true error will be the probability of making a mistake given our hypothesis, the one that we selected, and the probability of this hypothesis making a mistake is the probability of giving us a class that is different from the true class. So if our hypothesis is classifying, for example, in class 1 these examples, but actually these examples are the ones that belong to class 1, we have some errors here where we are misclassifying some examples. Now, one thing that we know is that we cannot directly observe the true error. We cannot measure this probability because this would require having access to the whole universe of examples. The learner can only measure the empirical error. This is what we measure on our sample S, on the training set, and we measure the error there. And we cannot reasonably demand that the true error will be 0 because we don't have all examples in our training set. So there may be several hypotheses that seem correct on the training set but make mistakes outside the training set. Sometimes the examples may actually be misleading. There may appear to be some correlation between the classes and the examples we have, but this just happened by chance because of those examples. So in general, we can expect that even if we can have a 0 error on the training set, so if our empirical risk is 0, we still have some error outside the training set. So this is the general idea when we take from these boundaries of the probabilities and these reasonable assumptions that we cannot get everything right is probably approximately correct learning. It's approximately correct because what we can expect is that the true error of the hypothesis we chose is not larger than some small number epsilon. It's not 0, but we can expect that it's small. So it's below some epsilon that, for example, is no larger than 1/2, and so we are performing better than chance, but it can actually be smaller. It's just that we cannot demand that it's 0. So it's approximately correct. We have a small true error. And we cannot even guarantee 100% sure that it will be approximately correct because we don't know the true error. We are just estimating based on the empirical error. So actually, the reasonable requirements here is that our learner is probably approximately correct. And this is the more formal definition. This means that the probability of the true error of the hypothesis our learner chose being smaller than some small value, or being no larger than this epsilon, this small value, must be larger than 1 minus this delta, which is another small value. So it must be, you must have more than 50% probability of having less than 50% true error. So we can think of it like this. Of course, we can narrow down these requirements. If we decrease epsilon, we can think of being more and more accurate. And if we decrease delta, we can think of being more and more probable that we are within that accuracy. And we consider a probably approximately correct learning to be efficient if the complexity of the computations, of the time running and requirements, is polynomial in 1 over epsilon and 1 over delta. So as we reduce this, the complexity increases, but increases polynomially and not exponentially. So this is the idea more formally of what we can expect to achieve with machine learning or this supervised learning when we're trying to classify something or predict something. We can expect our learners to be probably approximately correct. Now, in this, to see where this leads us to, we're going to assume that the hypothesis class is finite and that it contains hypotheses for which the true error is below epsilon. Note that if there are no hypotheses in the hypothesis class that meet this requirement, then there is no chance that we're going to find one with that error. So, and we can train and test from examples taken from the universe with the same distribution. So under these assumptions, let's see where we can get to on the boundaries of our true error, and depending on the size of the hypothesis class, the size of our data set, and so on. So let's start with this concept of version space. A consistent hypothesis is a hypothesis that it has an empirical error of 0. So if we can classify the training set with no error, we have a consistent hypothesis. The version space is the set of hypotheses in our hypothesis class that are consistent. So the version space is the set of consistent hypotheses in the hypothesis class. That is, hypotheses that have an empirical error of 0. Now, it must be true that a consistent hypothesis minimizes the empirical error, because we cannot have an error below 0. So a consistent hypothesis minimizes the empirical error. And if the learner is consistent, then it will output consistent hypotheses. That is, our learner can give us hypotheses that do not make mistakes in the training set. This is the idea of a consistent learner. There are two possibilities then for this version space. We say that it is epsilon exhausted if all hypotheses in the version space, that is, all hypotheses that can classify the training set with no errors, have a true error below epsilon. So if all hypotheses in the version space have a true error below epsilon, then the version space is epsilon exhausted. If at least one hypothesis in the version space has a higher true error than epsilon, then the version space is not epsilon exhausted. Now, note that we can tell if a hypothesis is consistent or not because we can measure the training error. But we cannot tell if the version space is epsilon exhausted or not because we cannot measure the true error. So this is unknown for the learner. The learner does not know in which situation we are. Either all hypotheses in the version space have a true error below epsilon, or there are some that do not, but we do not know which is the case. But we can try to estimate the probabilities of that. So what is the probability that there is no hypothesis in the version space with a true error greater than epsilon? We can try to estimate that. So consider that we have a set of hypotheses with the true error greater than epsilon. So these are hypotheses somewhere in our hypothesis space that have a large true error. The probability that one of these hypotheses is consistent with one example, that is, the hypothesis classifies one example correctly, must be below 1 minus epsilon. Because if the true error of this hypothesis is larger than epsilon, the probability of classifying some example correctly is smaller than 1 minus epsilon. So the probability of one of these hypotheses classifying all the m examples in our training set correctly is smaller than 1 minus epsilon raised to the power of m, because it must classify the first one correctly, the second one correctly, and so on, all of them correctly. So the probability of having at least one hypothesis for which the true error is larger than epsilon, consistent with all the examples in our training set, must be smaller than the number of hypotheses that have a large true error. So this k is the total number of hypotheses that make lots of mistakes, so to speak, multiplied by 1 minus epsilon raised to the power of n. Because this comes from that bound that we saw before. This would be the probability of one hypothesis doing this, or another, or another, or another, and this must be lower than the sum of the individual probabilities. And if the individual probabilities are all below this, then this must be all below the number of these hypotheses multiplied by that term there. Of course, we don't know what k is, because we don't know how many hypotheses in our hypothesis class have a true error larger than epsilon. So we don't know what the k is. But we know that k cannot be larger than the size of the hypothesis class. So we can put a boundary here. We know that this must be small, cannot be larger than the hypothesis class multiplied by this term. And notice here that all of these bounds are safe. This must be the case, but we are getting increasingly large boundaries. So in practice, this will not have not be useful if you want to estimate the errors of the classifiers you're training. This is just a formal approach so that we can understand more rigorously what is happening in these cases. So we can do this manipulation here. 1 minus epsilon is smaller than e raised to minus epsilon for all values between 0 and 1. So since epsilon must be between 0 and 1, we can do this transformation here. And so we reach this conclusion that the probability of there existing one hypothesis that is in the version space, so it's consistent with all the examples in the training set, but at the same time having a true error at least as large as epsilon, cannot be greater than the size of our hypothesis class multiplied by e raised to minus epsilon m. So this m is the size of the training set. So this is the upper bound on the probability of our learner not being able to discard all hypotheses that have a true error larger than epsilon when it looks for the minimum empirical error. We can also use this to compute a lower bound on the number of examples. The consistent learner, the one that gives us consistent hypotheses, will need to, with a probability of 1 minus delta, obtain an hypothesis that has a true error below epsilon. So we can replace the values there in the expression, and basically we get to this point. So this is the important part here. The probability for this kind of learner to give us a hypothesis that has a true error no larger than epsilon is greater than 1 minus delta, this initial expression. This means that there must be this relation. M must be greater than 1 over epsilon multiplied by the logarithm of the size of the hypothesis class divided by delta, or we can look at this in terms of epsilon, the true error, the boundary on the true error as a function of m. So basically, we can see this with this, that if we want the true error to be bounded at some limit with some probability, 1 minus delta, then we need to increase m to be able to do that, because as we decrease the error, m must increase. Or if looking the other way, if we increase m, then we decrease the error. So this is an intuitive notion that if we increase the training set, we get better results, but we can see this more rigorously formalized by looking at the boundaries of these probabilities. And note that these are all probabilities, so it's not a certain thing. We are dealing with the probability 1 minus delta of this happening, of not going over that epsilon in the true error. Okay, so this assumes that the best hypothesis that we chose has an empirical error of 0. But we can extend this for empirical errors greater than 0 by looking at the error as the average of these Bernoulli variables, which are whether or not we get the classification wrong. And so we can use these Hufting inequalities and actually extend this expression for cases where our learner is not consistent. So there may be some error in the training set still. And in that case, we basically get this expression here. So you can do the derivation, but the expression is similar. The only thing is that we get 2 epsilon squared here instead of just the epsilon, but the idea is the same. If we try to reduce the upper bound on the true error with some probability, then we need to increase the training set, or we need a smaller size of hypothesis class here. Okay, so we saw in the beginning that we need some inductive bias in order for our learning algorithm to be able to generalize. This was, for example, if we do linear we have a linear classifier, the inductive bias is that we are only considering linear frontiers between the classes. If we do something like that, in all of those cases, we are restricting the hypothesis class so that the number of hypotheses does not cover every possibility. So this is the inductive bias. But let us suppose that we have no inductive bias. We create a classifier or a hypothesis class that has no inductive bias, so no limitation whatsoever. And this can be done. Suppose that we have a universe X of points. We want to find a hypothesis that classifies X, each example, into 0 or 1. And our hypothesis class is the set of all subsets of X. So all subsets of X are in our hypothesis class. This means that any combination of examples being in class 0 or in class 1, we can find in our hypothesis class, because we have everything there. There is no inductive bias. So in that case, the number of hypotheses in our hypothesis class must be 2 raised to the number of examples in our universe. This is the total number of hypotheses there, because each hypothesis basically can say that this example belongs to class 1, this example belongs to class 0, and so forth. So we have all the combinations of zeros and ones there, and this is 2 raised to the number of examples we have. So this is the size of our hypothesis class. If we look at the requirements for having a probability of at least 1 minus delta, that our true error does not go above epsilon, then we need to have this many number of points in our training set. And if we replace here the hypothesis, size of the hypothesis class by this expression, and we simplify the expression here, we reach this expression here at the end. So we need to have at least as many points in our training set as the total number of points in the universe of points, divided by 2 epsilon squared, and then multiplied by the logarithm of 2 over delta. And since we want delta to be a small number, because this is the probability delta of going over the limit of the error that we want the epsilon to be a small number, because epsilon is the difference between our training error and the true error. So m must be quite larger than the total number of points in the universe. So this means basically that if we have no inductive bias, then the upper bounds of our true error really explode, and it's impossible to get a training set large enough to be able to generalize. Of course, these are, in these demonstrations, the upper bounds are all guaranteed, so they may not be very realistic, but this gives us a more formal representation of this intuition that unless we constrain our hypothesis class and we create this inductive bias, we cannot use it to generalize. It becomes too loose, too powerful. It can represent anything, and so we cannot conclude anything about what comes outside our training set just because we chose that hypothesis for the training set. So this is an important thing about learning, is that it's important that the hypothesis class is not too powerful, otherwise we cannot generalize from the training set. Another thing that we can look at with this formalization is the bias-variance trade-off. So let's consider the generalization error. So the generalization error is this difference between the error we have on the training set for the hypothesis that we chose and the true error of that hypothesis. So we choose one hypothesis by minimizing the empirical error. And this is what the learner is doing. We give it the training set, it minimizes the error on the training set and gives us that hypothesis. And now there is a difference between the empirical error of that hypothesis and the true error. But there is some hypothesis in our hypothesis class, let's call it H star, that is the hypothesis that minimizes the true error. Note that we cannot actually look for this one because we don't know what the true error is, and this may not be the hypothesis that we find by minimizing the empirical error. But there must be some hypothesis in our hypothesis class that minimizes the true error. We just cannot find it. So we know that the probability of the true error of the hypothesis that we found being below some upper interval on the empirical error, that is the empirical error plus this epsilon, this probability is at least 1 minus delta. This is the definition we got for the epsilon and the delta and so on. We also know that the empirical error of the hypothesis the classifier, the learner gave us, cannot be larger than the empirical error of the best hypothesis. Otherwise, if the best hypothesis had a lower empirical error, we would have found it when we minimized the empirical error. Also, we know that the true error of the best hypothesis cannot be larger than the true error of the hypothesis we chose, because this is the best hypothesis. This is the one that minimizes the true error. So when we combine these, we can get this expression, which is the difference between the true error of the hypothesis that we chose and the true error of the best possible hypothesis in our hypothesis class. So there is a probability of at least 1 minus delta that the difference between these two is smaller than 2 epsilon. Okay, so now combining this with the previous expressions, we can write an upper bound with a probability of 1 minus delta for the true error of the hypothesis the classifier gave us, decomposing into these two contributions. The smallest possible true error in our hypothesis class, so the true error of the hypothesis that minimizes the true error, plus 2 times the square root of 1 over 2m and so on. Okay, so this is similar to the expression that we found previously. And here we can see more formally this trade-off between bias and variance. So if this term is large, it means that there is no hypothesis in our hypothesis class that is really very good, because all of them have a high true error. And this is what happens when we have a high bias. Our hypothesis class cannot fit the data adequately, so there is no way we can find a good hypothesis in there. There are none. And when this term dominates, basically we are underfitting. We cannot find a good hypothesis to fit the data. But if we increase the power of our hypothesis class, for example, we increase the size, we add new hypotheses so that we can have better hypotheses there, then we are increasing the size of the hypothesis class. And so when this term dominates, we may have hypotheses there that are very, very good. So they have a true error that is very small, but now they are hard to find because there are many hypotheses that work well with the training set, and now this term starts dominating because those that we find by minimizing the empirical error may not be close to the best ones when we look at the true error. So this is what happens when we have high variance. We have a very large hypothesis class, this term starts to dominate, and the problem we have with the true error of the hypothesis we find is not that there are no good hypotheses in the hypothesis class. They may be, but it's hard to find them unless we have a lot of data and we can really narrow down the region for these hypotheses. So we can see here this trade-off between bias and variance in a more formal approach. Of course, so far we've been assuming that hypothesis class is finite. So all of this derivation we found so far assumes that we can measure, we can count the number of hypotheses in our hypothesis class. This may be true in some very specific cases. For example, if you are doing a decision using decision trees, you limit the depth of the tree and you have categorical features so that there are only a limited number of combinations of rules in the tree, then okay, this may be a finite hypothesis class. But in general, this does not occur. If you're using any classifier with continuous parameters, then in reality the hypothesis class, at least in theory, it's infinite. Well, in practice it's not, because you're using floating point numbers and they have a limited number of different values, but for all practical purposes we have an infinite number of hypotheses. We cannot use this kind of approach. So for more realistic cases, we need a different approach. The derivation for that is really outside the scope of the course, but I can give you the general idea. And it's based on this notion of shattering. We can see intuitively that even though we have a continuous set of parameters, so we can have an infinite number of lines, for example here, when we try to classify these two classes, all these infinite number of lines are actually equivalent, because given that the data, the points have this distance, we can create infinite lines here, but they all give us the same classification and they basically work the same. So another way of trying to measure the power of a hypothesis class, instead of trying to count the individual hypotheses, which we cannot do when the parameters are continuous, is to have this notion that many may be equivalent, and what matters is how capable they are of dividing the points, the data set, into different classes. So this is the notion of shattering. One hypothesis class shatters a set of points S. So these are points that we fix somewhere. If for any combination of labels we assign to these points, we can always find at least one hypothesis in the hypothesis class that is consistent with that. For example, suppose that we have 3 points here in a triangle. The points can all be at the same color, and if we have a linear classifier, it's trivial. We just put the line outside to one side and we classify the points all with the same color. If one point has a different color than the other two, we can also solve the problem. So if there is one red and 2 blue, we can draw the line there. If we switch the colors, we can just switch the side, but it's the same thing. And it doesn't matter where what the colors are for the points. If we are using a linear classifier in 2 dimensions, we can always shatter this set of 3 points. We can create sets of points that are impossible to shatter. For example, if you put 2 points in the same position, then it's impossible to shatter, because it will not be possible to separate them. But that is not the interesting part here. The interesting part is that you can create a set of 3 points that a linear classifier in 2 dimensions shatters. So this gives us a way of distinguishing these situations, because if you go, for example, for 4 points, a linear classifier in 2 dimensions cannot shatter 4 points. There is no way to place 4 points that allows you to separate correctly the classes using a linear classifier when you consider all possible combinations. There are combinations that you can divide. For example, if these two are red and these two are blue, then you can draw the line here. But there are some label combinations, if you have 4 points, that cannot be separated without error with a linear classifier. And there is no way you can place the 4 points that would allow that. So this gives us this notion of the Vapnik-Chevron-Jenkins dimension. So the Vapnik-Chevron-Jenkins dimension of hypothesis class H is the size of the largest set that this hypothesis class can shatter. For example, for a linear classifier in 2 dimensions, the VC dimension is 3. 3 is the largest number of points that you can shatter with a linear classifier in 2 dimensions. Note that there may be sets with smaller number that you cannot shatter for some reason, because you put them all in the line or something like that, but that is not relevant. What we want is to find the largest set that can be shattered. And now there is a long demonstration of this result. We are not going to go into that, but it's a similar thing that what we saw previously. So the upper bound of the true error of the hypothesis our learner gives us, the one that minimizes the empirical risk, with a probability of at least 1 minus delta, is this. It's the training error of our hypothesis plus a term that is on the order of this large expression here, but basically it's the VC dimension divided by m and then the logarithm and so on. So you have this m coming up here, dividing this. So the larger your training set is, the smaller this additional term will be. So the closer your true error is likely to be to the training error. But if you increase VC dimension, then you're going to increase this term, and so you can be increasing the generalization error. That is the difference between the training error and the true error. So this is our intuition that if we have more powerful classifiers with a larger VC dimension, then we will need more data to train them correctly. Otherwise, we will be overfitting. And we saw this when we looked at expanding the number of dimensions to use linear discriminants to solve more complex problems. So for a linear discriminant in dimension D, we can shatter D plus 1 points. If you have a linear discriminant in 2 dimensions, you can shatter 3 points. If it's in 3 dimensions, you can shatter 4 points, and so on. So basically, the Vapnik-Chevron-Jenkins dimension of a linear discriminant is the dimension in which we are operating plus 1. So this is why we could improve the ability to classify our training set, for example with logistic regression, when we expanded our data to higher dimensions. If we do those nonlinear transformations, then we put the data into higher dimensions, we increase the power of the linear classifier, and we can classify the training set. However, we can get into overfitting unless we have enough data for training, because of this relation. When we start to increase the power of the classifier, if we don't have enough data in training, then this term starts to increase and we get a true error that is significantly larger than the training error. Of course, we don't actually measure the true error, but we can estimate the true error with cross-validation or with the test set or something like that, and we see that we are making more mistakes outside the training set. So here we can understand more formally what is happening when we are increasing the power of the classifier. Okay, so to sum up, this has been a very dense lecture, but the idea is that although this is not used in practice, you're not going to actually compute these bounds or look at apply these expressions in practice. This foundation, more formal foundation for machine learning, allows us to understand better these somewhat vague intuitions that powerful classifiers need more data and things like that, or the trade-off between bias and variance and such. So what we saw here was how to, or just an outline, a brief look at how we can give a more solid foundation on these intuitions. Why we need inductive bias, because not having inductive bias means that the hypothesis class is hugely powerful, and so we cannot generalize. The bias variance trade-off. So if we want a hypothesis class that guarantees that we have a very good hypothesis there, then we need a powerful hypothesis class, and this will also risk increasing the variance, and so increasing the generalization error. We saw this idea of shattering and the VC dimension when we apply the same concepts to continuous models, but the basic idea is the same. And an important aspect of probably approximately correct learning is that you don't have guarantees. What you have is a large probability of having a small error if everything goes well. So if you want to read more on this, chapter 7 of Mitchell up to section 7.4 has this first part for finite hypothesis class. It's a bit outdated, but it's a good explanation. You have some coverage of this also in Alpiden if you want. So let's take a small break and we continue at 4:55. Okay, so about 10 minutes. See you soon.